Okay, so we're going to talk about energy problem solving today. As we do pretty much with everything, right? We start with basics and then we learn how to solve problems and then we just go from there. So from last class, right? Just again a pretty common review. This is our most important equation that we're going to talk about probably all year long, right? And remember, we don't necessarily have to memorize. It's not about memorizing the variables and how they're added together, but it is memorizing that, like, the initial energy plus any energy transfers is going to give us our final energy. Right? And what are the three ways we can transfer energy? Heart? Not temperature. Heating, radiating, and working. Last class we talked about these LOL bar charts.
LOL.
LOL.
It looks like
LOL, because it looks like an L,
Darn.
an O, and an L.
Darn.
All right, so when we look at these, what do we put at the bottom? What are the bar charts for? What do the bar charts tell us? Good, the different types of energy, right? Where's the energy stored? Is it stored in kinetic energy? Is it stored in elastic potential energy? That's not determined, right? That's something that we know. But then we determine how much of each energy account there is. How much is stored in each account. And right now, before we know how to calculate any of this stuff, this is pretty arbitrary. What goes in this circle here in the middle? The system, right? What goes into our system? So if we want gravitational potential energy, we have to include the Earth, maybe an object, a spring, whatever it could be. It could go on and on. Whatever you're looking at is what tells what we're in a system. Could you have energy stored somewhere else besides your system? Yes. Yeah, you could have energy stored in something that you're not looking at. But again, when we talk about the energy stored in the system, it's important for us to identify what we're looking at. And then we have our final energy. So if energy gets transferred, where does the energy now store? Something like that, maybe. Maybe elastic potential energy was unchanged. So again, this is really just setting it up like our conservation of energy equation. This is our initial energy. And all types and forms of initial energy that we have here with this first bar chart. No? Good catch. This would be any type of transfers of energy that we have. And then the last bar chart tells us our final energies and how much of them we'll have. Now this bottom equation that we have here, yes, that's the conservation of energy equation for any situation. But what are we going to do with it once we have a specific situation to look at? We're going to narrow it down. So maybe we'll talk about the different types of energy that we have. Was there any energy? If there's no energy transferred through working, then we can ignore that. And same thing with heating and radiating. So let's get some practice really quick. Just again, make sure that we're feeling comfortable with these LOL charts. So if you have an ice cube sitting on a table, and then sometime later the ice cube starts to melt, what is your LOL chart going to look like? So again, I want you guys to write this down. So get out notes. Write down an LOL chart.
So it's like the ice is melting.
Yeah, so you have a piece of, like an ice cube, and then you have don't write this on the whiteboard. I want you guys to write it in your notes. No. Okay. Why don't you have a pencil? Go back. I want you to write it down in your notes. All right, so for the ice cube, what's our system, do you think? What would you choose our system to be? I would say the ice cube. And then maybe the Earth will also add in there in case there's some gravitational potential energy, but there probably won't be, so we might be able to ignore that. What type of energy do we have at the very beginning? Thermal? What I think we called that is if you have ice just sitting there, when you have a solid, what are the particles in the solid doing?
They're not moving, they're cold. No.
They are moving, right? They're moving back and forth, right? So they're vibrating. So we call that the internal energy. And what determines the internal energy of a system? The temperature, right? Something with a higher temperature has more internal energy, right? We have more vibrational energy. We can sometimes call this thermal energy, but I'm going to say focusing on internal energy right now. So how many bars are we going to say, or how many blocks of internal energy do we have? 2? Do we have to have 2? Do we have to have 3? We're going to say there's some, so I'll say 1 bar
What kind of
of internal energy. Internal energy is the vibrations inside of the particles. That's what makes up the temperature. Now, is there any energy transferred into or out of our system? So how would it be transferred in? So I guess at the very end, do we have more or less energy than we started with? So if we have more energy, that means energy must have been transferred into our system. How was it transferred into our system?
ice?
Not radiation. Right, so we said, when do we have heating? Heating is when we have a temperature differential, right? When we have 2 objects that are different temperatures, the hotter object is going to transfer some internal energy to the colder object. So this will be the first instance in which we see some positive heating being done. Because it's going into our system. So we had the same amount of internal energy we had before. But we're also adding 3 more blocks of energy that came from heating. So that must have come from our surroundings.
So the surroundings don't, so that's not Earth, like that's outside of the system.
That's outside of the system. Right, that's why I wrote it outside of the system. So now we have to write our conservation of energy equation. We know it's going to be initial energy plus whatever energy was transferred, giving us our final energy. What type of energy do we have initially?
Internal.
So we have our internal energy. Were there any energy transfers?
Yeah.
Oh, heating.
We were heating, right? So we have some positive heating. And what type of energy do we have at the end? Which is internal energy. So we have more internal energy. All right, cool. But it's stored in the internal energy of the material. So what's the difference between a liquid and a solid? Right, when you talk about the particles that make up a liquid and make up a solid? So solid, they move slower, right? It's just tiny vibrations. But liquids are free to move all over the place, so they have more energy. So that's why we have some liquid ice and some solid ice. So we're going to have more energy in the liquid. Again, that was kind of arbitrary. But we would have other reasons to believe and figure out how much energy was transferred via heating. But for right now, we'll just say that it was 3 blocks. We could do the same thing for hot coffee if we put that into a ice bath, right? So if you have a cup of ice cold water and then you put coffee into that, we could do the same thing. What's our energy, what's our system going to be here?
I guess just the hot coffee. Yeah. Wait, can you like sum up everything?
Sure, we could say coffee. I think if that's what I'm looking at, it could be the coffee. I don't really care about the Earth in this situation because there's no change in height, so that's not going to be an issue for me.
Why did we care about Earth?
We didn't, but we wrote it down anyway. It didn't change anything. Sure. Just for kicks. So here we have internal energy stored.
Is that all you have in the system?
I'm just looking at the coffee. How much internal energy if it's hot coffee?
1 block, 2 blocks.
Probably more than the ice cube, right? So we should say maybe a lot. So for me, a lot's going to be 4 blocks. Are there any energy transfers? There's going to be transfers of energy out, right? There's a temperature differential, right? There's hot coffee and cold surroundings. So is there energy going to be transferred from where? From high to low, right? From hot to cold, high energy to low energy. So we're going to transfer energy out of our system. And, you know, we'll say it's 3 blocks again. Now, is this positive or negative? Negative. How do you know it's negative? Because it's out of the system. So we're transferring energy out of our system.
Why is it negative?
Because it's heating. So we're transferring energy to the ice bath. So our internal energy at the end would be what? Specifically 1 block, right? If we transferred 3 blocks out, then we're left with 1 block of energy.
So you can't.
I explained the 2 block.
Don't you have to write like for the one above you added the blocks for heat? Don't you have to like somehow show that you took this away?
I did, right? You see how it's from starts in the system, and then it transfers out of the system.
But in the graph.
Well, the graph now shows 3 less bars. It had 3 bars before that, and now it has 3 less. Now, this equation looks like we're adding energy to our system, right? But what do we have to remember? This is negative heating. I would rather you not write minus, but recognize that heating is going to be negative. So I would circle it and say it's going to be negative. Right, because we're transferring energy out of our system. And if we're transferring energy out of our system, that means that the final energy must be greater than the initial energy.
Why would the ice bath not be part of our system?
If we did include the ice bath, what would happen here?
Everything would be within the system, so there would be no.
There'd be no changes. So if we include the ice bath, then there's no problem. There's nothing that we can get out of it if the ice bath is included in our problem.
Wait.
So if we included the ice bath and the coffee in our system, then that means that the energy transfers from inside of our system to inside of our system. Sort of like if you were looking at your family's money, like the total amount of money that your family has, and they give you $3, your total amount of money for the family hasn't changed because your family still has that $3 if you include yourself.
Gave $3 to your neighbor.
That'd be different then because they're now no longer in your system. But if you were looking at then maybe the amount of money on your block, then you transfer money to your neighbor, and that stays within the block. So yeah, so it all depends on what you're looking at. Because eventually, what if we included everything in the entire universe into our system?
So no change.
There'd be no change ever because energy, the total amount of energy in the universe is always the same. All right, how about a plant growing? What type of energy do we have stored in a plant?
Chemical.
Chemical potential energy, right? That's what we get when we eat a plant. So we'll say it's a little bit amount of potential energy. Are there any energy transfers while after to growing? Good. Right, if the sun, which is outside of our system,
How do you get chemicals from it?
well, it's stored in chemical potential energy. What type of transfer is this, though, from the sun? Radiating. So we must be adding some energy via radiation.
How do you know how many blocks that
Again, it's kind of arbitrary right now. We haven't decided to, we haven't solved any problems yet. So how much chemical potential energy is there in this plant now? 5 blocks, right? So we started with 2. And then we transferred in 3 more blocks from radiation. So how does a plant grow? What's it called? Starts with a P. Photosynthesis, right? Where it absorbs the sunlight. And then what happens with the sun? It takes the energy from the sun, and then stuff happens, chlorophyll does stuff, and then it has energy. So I'm not a biology teacher. You're probably going to want to talk to Dr. Krug about that, and he can tell you all the details about it. But yeah, so we're definitely taking energy that it's absorbing with its leaves and then transferring it to some stored chemical potential energy. Yeah. What happens if a kid slides on a carpet and gets a rug burn? First of all, what are we looking at? What's our system here? I think I'm probably going to say the kid. That's my system. We can say the earth.
Wouldn't that be the ground?
So when we say the earth, that's just so we can include gravitational potential energy. So I wouldn't include that as the ground, because he's on a carpet.
What about carpet?
So I don't want to include the carpet.
Because that wait, why for the one before the plant? Why is this like not in our system?
Again, because it just wasn't. So we said the sun wasn't, so that means that there was radiation in. If we include the sun in our system, then that means there's no change for anything on Earth, because the sun is where we get all of our energy from.
That'd be transferring energy from our system to us.
So what types of energy do we have at the very beginning? I'm not going to say thermal yet, right? Because the thermal would be something that we've dissipated, and we haven't dissipated any energy yet. So it's going to be kinetic energy, right? He's sliding, he's moving. How much? 3 blocks, why not? Now, are there any energy transfers? Friction from the carpet? That's a force, that's not an energy transfer. What type of transfer do we have?
Dissipated.
Transfers. Remember, there's 3 types of transfers.
Sorry.
Velocity, kinetic
Work.
energy.
Heating?
Work.
How is there heating? What do we say causes energy transfer through heating?
When we rub,
What do we say transfers energy via heating? Like how does that happen?
when things rub together and spit out. No?
How does energy transfer via heating? We just talked about it a second ago. If there's a difference in temperature, right? If there's a drastic change in the amount of temperature of your surroundings compared to the amount of the temperature of your system, then there's going to be heating transferring energy. Now, is there a drastic change in temperature from the kid's arm to the carpet? No. So where is this energy transferring? How is it transferring? Because essentially it's going to slow down. So it must be work, right? Because work is... Rachel, you said everything.
I said
So
work before.
you could just say, oh yeah, I said words. Cool. So if we start with kinetic energy and he starts to slow down, that means he has less kinetic energy. So where did that energy go? Well, it must have been transferred out of the system by the force of friction, so by working. So we'll say 2 blocks.
You have to say what makes it. You said carbon.
Yes, carbon. So this is our kinetic energy. I thought we said that it would, whenever we had something sliding across the floor, it went to dissipated energy.
That's what I thought.
So why didn't it go to E dissipate or E thermal? Because the carpet's no longer in our system. So yes, that energy still is stored in dissipated energy in the carpet, but the carpet's outside of my system, so it doesn't matter to me right now. So if we had to do this, what would our energy conservation equation look like?
EK plus W. And you know what that's negative.
And then we note that this is negative working. Because what does negative working tell us again?
Energy's being taken out of the system.
Energy is transferred out of the system. If energy is transferred out of the system, then that means that our final energy must be less than our initial energy. So now we're going to actually talk about solving information, solving problems with this stuff. So let's do this. So we have a spring. We talked about this last class. We did a bunch of examples. We have a spring that's not stretched at all, and then a mass stretches the spring after it's been dropped. The initial types of energy that we have, it's all gravitational potential. So here I'm going to say 4 blocks of gravitational potential energy. My system being the mass, the spring, and the earth. At the very bottom, though, when it's stopped, what types of energy do I have? Elastic potential energy. But it's at the very bottom, so there's not going to be any gravitational potential energy. So it looks like all of our energy is going to be elastic potential energy. Cool. So were there any energy transfers into or out of our system? So in this situation, our initial energy must be the same as our final energy. Now I'm asking you, what's the spring constant? We could probably make this conservation of energy equation a little bit more specific. So how would we make it more specific, Dom?
Oh, well, you could do mass times gravity times iron plus 1 half spring constant exchange conditions.
Good, so I'm going to take it one step prior to that. We'd say that our initial energy is all gravitational potential energy, and our final energy is all elastic potential energy. So if I wanted to figure out what the spring constant was, what might help me figure out the spring constant? Like Dom said, we know that this is the elastic potential energy is 1/2 K, which is the spring constant, times the amount of stretch squared.
So the amount of stretch.
It's the amount of stretch in the spring.
Is the same as time.
So in this situation, what's our initial energy going to be?
1/2, just energy.
Good. So what's the mass times the gravitational field strength times the height? Someone with a calculator might help me out. Or someone that knows what 6 times 9.6 is. So we start with 58.8 joules of energy, and we're going to end with how much? Better be the same. We said it was the same amount. So our initial energy is 58.8 joules. How much did the spring stretch?
3.
It has to be 3 meters in this situation, right? Because we started at 3 meters high, and then we ended at a height of 0. So the stretch was 3 meters. So 3 squared is 9. Half of 9 is 4.5. What's our spring constant going to be? Someone tell me. We'll say 13.1.
How are we getting so many different?
13.1 newtons per meter, sure. Oops, it's supposed to be there. So everything's come full circle now, right? We've started with solving problems using just kinematic equations, our motion equations. Then we found out that we can use forces to solve the same types of problems. And now we can use energy to figure out velocities and forces and whatnot. So if we can use all of these things, we're now at a third way to solve these same types of problems we've been doing for a long time. Some strategies, things that we want to remember. If we're going to solve a problem using energy, we probably want to draw an energy LOL chart first. Right? That helps us identify the different types of energy and how much and how the energy transfers into or out of our system. And then we're going to write our conservation of energy equation and then make it more specific for our situation. So if I start with the original equation of our initial energy plus any energy transfers equaling our final energy, I'll never figure out the spring constant in the spring. But when I make it specific and talk about what types of energy transfers there were and what types of energy we have to start with, it becomes easier for us to make that happen. So what we're going to do now, we're going to work on this on our own a little bit. We have three options. So for people that are feeling the challenge, you can start with the first option, which focuses more on the energy calculation basics first, and then gets more advanced, and then we end with LOL charts and problem solving. But we start with more basic kind of scaffolding to get us up to there. You have the second option, which starts with a quicker intro to the calculations and then goes straight to the LOL charts and problem solving. And then the third option, which would probably be more advanced problems, less of the intro with calculations and really more just getting into the problem solving itself. So come up and grab one of these choices. So a lot of them, they will share similar questions, right? The questions will be the same in all of them. Some will have more questions that aren't in others.
Is this the third one?
That's the third one.
Somebody pass me.
May I use the restroom?
Yes, you may use the restroom. Now would be a good time. Which one do you want, Carter?
No, this is the first option.
First option is on the left. So we're going right to left. 1, 2, 3. One,
That's
two.
just not American.
What does it say on your hat?
I don't know. What does it say?
It says I'm a cowboy.
Higher level.
Can I
You would
work
have
on
that.
the first one?
Yes, guys, you should check your answers to the homework. There are answer
What?
keys on the front of the board.
So I can do the one.
Which is the
You should do that because you can't do this.
This one.
Okay, sir. I was just asking. Like, you calm down.
Did you untop?
No.
Whoa, 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 whoa. Whoa.